Мизуно реактор.
Yeah.
So these are slightly better diagrams of what's going on. I'll spend a little more time on this diagram later. These are the voltage pulse connections on each end. The rod, the reactor tube goes through the middle here. Around that is a steel gas containment tube, which is generally filled with 9 atmospheres of hydrogen. And then there's a 2.5 kilogram heat spreader here for the calorimetric reasons. There are temperature sensors. There are thermocouple in the middle of the heater, in the middle of the reactor tube. There's a thermocouple out here. There's a thermocouple coming in here. Outside of this heat spreader is insulation. And then there's another aluminum cylinder with a couple of thermocouples in that. And then an acrylic cylinder around the aluminum cylinder completes the mass flow calorimeter. And the temperatures in the mass flow calorimeter are measured with RTDs and flow rates with standard flow controllers. Down here is a photo of that, slightly out of proportion, but the heat, you can see the heat spreader, you can see this temperature sensor coming in here, and these two are band heaters which are on the outside. They're used in some of the experiments I'll describe, and in the others we'll be using the internal heater in the inside of the reactor tube. So as I said, static, about 9 atmospheres of H2, operate from 200 to 600 C. We keep the temperature or the power constant. They keep the temperature or the power constant. I should explain that I am still maintaining my independence from the Berlin Energy Corporation. And then they control the pulse or the heater power at constant using the PID approach. And yes, the actual pulse power is measured directly, as well as the fixed pulse width and amplitude. So usually, as I showed in that diagram, the amplitude is kept constant during an experiment, as well as the pulse width, and the repetition rate is changed in order to ramp the power. Calibrations are usually done with DC along the nickel or with pulses of lower voltage. Unfortunately, pulses at lower voltage, even at higher repetition rates, don't raise the temperature enough, so heater is usually added. And so we like to operate in the 200 to 300 C range. And there are several different types of calibration that we use. And then the stimulation is with those high voltage pulses and the appropriate repetition rates. Working on more efficient pulse generators, all of that. The important part down here in the bottom is we do a double check. The amount of power lost in the generation system is significant, and they're working on getting rid of that and hopefully not blowing up too many boards as they're working on it. But in order to keep everything working, we actually have to run mass flow calorimetry cooling the switching transistor, and also mass flow calorimetry cooling the termination resistor. And interestingly enough, not interestingly enough, but fortunately enough, if you take the power measured at the power supply, subtract the mass flow calorimetry power across the switching transistor and that across the termination resistor, you get a number very close to what you measure with the oscilloscope. And this slide shows that. I won't spend too much time on it, but the blue is the number measured by the oscilloscope directly, and the red is that measured by the mass flow subtraction from the power supply. Obviously, mass flow calorimetry is a little noisier. That's a look at the computer interface. Only 2 points I want to make is there's very good control down here, temperature and the pulse power can be controlled by a PID. And notice the sequence tab up there. Very few of these experiments are run manually. Set up a sequence of up to 500 or more steps and just let it go. And some of the experiments run up to 100 hours. So this is what one of the mass flow calibration looks like. This came from actually those external band heaters that I pointed out on the outside of the heat spreader. And as you can see, the heat put in, these are 6-hour steps, and the calorimetry from, I'm going to refer to mass flow calorimetry from the outer jacket. So between the aluminum and the acrylic cylinders is the main mass flow calorimeter. So when I refer to mass flow calorimeter power, that's where that is measured. And you can see it follows quite well. The system doesn't quite come to equilibrium in 6 hours, but those can be averaged well enough to be used in stimulation. And this is just another experiment. This one, these are 8-hour steps. So the blue is the heater, this is DC joule across the nickel. So we passed the DC current across the nickel and measured the power directly, and that's what's on the blue line on the left axis. We had a room temperature issue, that's what the yellow is, and so that made the raw mass flow calorimetry in red look bad. So we corrected for that and corrected for the efficiency, and it comes up here again as well as the other. The black line against the right axis tells you about the temperature of that reactor too. And this is a summary of that last slide where I've taken the last 5 minutes of each step and all of the powers and the temperature. And so you can see the red dots are the noisy room temperature driven issue. The green dots are corrected for room temperature. The green circles are corrected for room temperature and efficiency. And the blue line is the input power equals the output power. The black dots are the numbers from the temperature, again, on the right axis. as you can see, we can trust that calorimetry. And unfortunately, I don't have any data to show from the mass flow calorimetry, so I'm going to change gears here and move into the heat flow operation. And I should mention here that Berlin has been using the system identification methodology that was published in Nature Perspective by the group funded by Google. And they have been working very closely with the people in that group who developed this system ID methodology. And so some of that goes into many of the data that's been reported on the web page. I won't talk about those. Those are actually very complicated, and I'm not into that level of mathematics. So I'm going to talk about a slightly watered down version of the system ID. But so the calibration is generally done is like 2-hour steps, and like I said, we usually have to add heat in order to maintain the temperature above 200 C, adjust the repetition rate as mentioned before, and then after getting the calibration parameters, the stimulation is usually done with another automatic sequence in 5-minute steps, just pure pulses, no heater. And then the other way we can do that, we can compare a reactor tube that we know has never shown excess power. Yes. I guess I will know when it's time to quit. And so we can compare what's called a null. We found that out at SRI a long time ago. Your best blank is one that you know is dead, does not give you excess power. Just put it back in and run it, and it'll tell you what your calibration is. And so the 100-hour sequence, like 52-hour steps for calibration, and then a 96 through 485-minute steps is a 40-hour stimulation. And we can compare the calculated output power with high voltage and low voltage pulses. So back to this diagram and the model. I really do have to mention Bob Higgins presented something very similar at ICCF 21. Like I say, this is the watered down version of the very complicated system ID, which requires MATLAB and a system identification module. And yes, difficult to follow. For me. Not for the people who run it, and I'm sure for most of the coders in the room it's trivial. But anyway, so the power coming in, like I said, goes through those two connectors. The temperature of the reactor tube is right here in the middle of the reactor tube. The temperature, what we call the block, is right here. The conductance between the tube and the block is well known. It's just pretty much the hydrogen gas. The conductance between the block and the surroundings is out here is the known temperature. That's the insulator in there. The heat capacity of the tube is well known, rather small, only about 50 grams of mostly alumina. The heat capacity of the block is much larger. It's 2.5 kilograms of stainless steel. So same model. Should mention that those 4 2Cs and 2Ks are everything that's being adjusted in order to reach the calibration. Now, they're not simple. If we did them simple, the fit would not be so great, but the numbers would be very close to what you can calculate for first principles for those materials. But they're binomial in that they have a constant, 1 times temperature, and another 1 times temperature squared. And interestingly enough, as I'll show in a second, the equations put all of them against temperature again, so they're really third order, first order, second order, third order. And with 4 of those and 4 constants and 3 third order, you get about 12. You get 12 adjustable parameters. So those are the equations, and I'm not going to go through them, although I spent a lot of time having the person who does this explain it to me, so I could explain it to anybody. But in the end, you minimize the difference between the measured temperatures, both on the block and the tube, and the calculated temperatures by adjusting the 12 parameters that represent those physical devices. Oh, and if anybody hasn't read these, anybody doing calorimetry really should go check those out. And anyway, we use those to solve for the parameters, and then check the parameters in the calibration where we're not expecting any excess power, and you essentially can't see it, but they're sitting right on top of each other. In there where we had a little problem, you can see where they separate. So the calculated and measured temperatures are sitting right on top of each other. And as a double check, we did the, oh, I missed another one, okay. Calculated and measured power, input and output power, and there's supposed to be a squiggly red line on top of that, but it's an extremely good fit. Unfortunately, you have to trust me on that. Oh, and the 12 parameters are down here. And like I said, interestingly enough, they get, particularly the 0 parameters, correlate very well with what you calculate from first principles for the materials. And so there's a stimulation experiment, and at lower powers and lower temperatures, there's just a little bit of excess power. The blue being the input, the orange being the calculated output, and as you get to higher powers and higher temperatures, you get a COP, a ratio of about 1.5. We do this again in a different, in the same type of calibration, but a different type of, it is working, it is trying, there we go. So that looks identical to the last calibration. And so, yeah, I won't spend any time on it. This is a different reactor tube, and so the parameters have changed due to that. And then the stimulation is different. So again, this one is that 40-hour stimulation. There are 485-minute steps in this. You can see a little bit of quantization in the input power and in the output power calculated by taking those 12 constants, putting them into the temperatures that are measured, using that and minimizing, just simply taking those 12 constants, putting them into the equations to give you the power, the calculated power, and that's what we see here in the orange plot, and that's about 1.6 COP. And as a good test when you run these is if they come back to 0 or wherever you are, sometimes we'll have heater power here, and if the input and output powers come together, we know that the model has come together properly. Running a little fast, so let me go over the results. So they've been stimulated by electrical pulses, like I said, high power, high voltage, high current, between the nickel and the copper across the dielectric. Experiments are all in hydrogen gas. The gas is static between 200 to 600 C. One way is to compare low voltage and high voltage pulse power. The other way is to use heater or DC. They stopped doing the DC. That was my idea, but kept melting the ferrules, so we had hydrogen leaks and occasional hydrogen fire, but that's okay. We fixed it. So the isoparabolic calorimeter can operate, like I said, in either heat flow or mass flow mode. And when we're operating in heat flow mode, I didn't mention that we turn the power way up, the flow rate way up on the mass flow calorimeter, so the temperature in the reference temperature is constant. And then when we operate in mass flow, we actually turn it down by like 2 orders of magnitude so that we can get a delta T of 10 to 15 degrees across that mass flow calorimeter. 500 experiments, 130 different cores. They've created 170, but 40 of them failed the bench test before they even go in. The COPs measured up as high as 2.8 were done using that sophisticated system ID model with a virtual mass and a virtual temperature, and like I say, I can't follow it, so I don't present those results or those methodologies, but I do believe they work very closely with the people who developed it to show that it is real. Still a lot of metallurgy and ceramic composition to work on, and working on mass flow calorimetry, see it from across the room analysis. Dave's been beating on me for a couple of years to get rid of what the engineers call parasitic losses, so that we can get 90% of the power from the wall into the tube. And we're working on that, and they're working on that. They're the electrical engineers. I'm the chemist. So yeah, the efficiency right now, get 100% efficiency on the block heater, 70% on the internal heater that I showed, and only 60% on the DC joule heating. There are good reasons for that that I can discuss in the future. And I have to thank these people. Particularly I want to thank the Anthropocene Institute, which allows me to work with them independently. And thank you for your attention.
John Paul, maybe have a microphone in the front here, please.
The phone? Yeah.
Oh, Brooks already has a microphone. But
Let's.
Yeah, can you specify the pulses that you put in? Like how much current do you put in, and for what is the pulse duration?
Okay, generally the pulses end up about 50 nanoseconds. And if I can go back to that chart, which without too much trouble. And that is actually quite low, the numbers on this chart. They've gone up, but the current coming in here, the current coming in is in the 50 to 100 amps, and the voltage is up in generally today the voltage is around 200 to 230, and the current is probably in the 100 amp range for up to 50 nanoseconds.
Thank you.
Yeah, sure. Yeah. In your system, you heat from the outside with the heaters.
Occasionally.
Yeah, but it could be better maybe to use a DC current directly added to the pulses to heat the film directly. It's more complicated maybe in terms of electronics, but that would simplify the system.
Yes, but we have a heater on the inside. We actually, right inside the tube, which it's a different length than the length of the nickel, so that messes up the calculation, but I think we can fix that. I think the easier way to fix that is to just move the calorimeter out and cover everything and go that way. But it's a good idea. I get beat over the head by the electrical engineers every time I suggest DC, but I'll suggest it again. I'll blame it on you.
All right, it works this time.
Do we have any other questions or comments?
Thank you. Maybe I did not just understand properly. You mentioned something like you have different reactor with different tube. How many reactors do you have with different design?
No, they're actually not meant to be different designs. There are 4 of them. One of them is slightly different. We're using it to test new methods. But the reactors should be very close to each other, but they're all handmade, and so they aren't identical. So they're different. And the tubes, the nickel coatings have different impedances, and different, so they'll have different conductivities. And so that's why there's a difference. Just the fact that the handmade reactors are not identical and the tubes are different.
More or less the geometry of these 4 reactors are the same?
Yes, yes. On paper, they're identical.
Well, on paper identical, but in reality it's a little
Not
bit
so
different
much.
because of handmade. And the second question is, have you considered other combination of fuel other than nickel pump?
Other than hydrogen?
Other than nickel?
They've tested different alloys, nickel, palladium, pure palladium, some of the titanium, but so far have settled back on nickel because it's given them the best performance. I personally would like to do a few more different things. Right now it's a little money driven.
We have another question.
Yes, some time ago I had a discussion with David Fierscheim, who is the financial director for WeWork, and he sent me some files in which it's put a comp of 3.6 for very recent experiment. So do you confirm these results?
Like I said, first off, I don't know about a 3.6 number. The best number that Fierscheim should be distributing is 2.8. And as I said, 2.8 is done in that very sophisticated system identification model, which I do believe, but I can't verify it because it's too complicated for me.
Francesco?
A question quite simple. Did you observe some strong variation when you apply the stimulation and without apply, means like of degradation of performance?
Only very rarely have they put any radiation detection equipment in the room.
Not means about radiation.
Oh, RF?
Not degradation of a performance when you don't apply stimulation for a long time.
I haven't seen that. One of the tubes has run for about 9 months, on and off, and it was off for about 3 months and came back and actually was even better. But that's just one tube, and